Good morning, everybody. Welcome to Hydraulics and Hydraulic Machines class. We are in Unit 4. Unit 4 consists of three parts. The first part is components of a hydroelectric plant, classification of turbines, then Pelton turbine, which is of impulse turbine, its components, its working proportions, its design, the velocity triangles, work, work done, efficiency, and problems. This all comes under part 1. Part 2 consists of the Francis turbine, same components, velocity triangles, working proportions, design, problems. Kaplan turbine, same components, their function, then basically working proportions, design, work done, and efficiency. And apart from that, in part 2, we have studied about the draft tube, functions of draft tube, then types of draft tubes, the significance of draft tube, and the efficiency of draft tube. So that completes part 2. So today we are now talking about or discussing about part 3 of hydraulic turbines. So in this, the first topic is the most important concept of hydraulic turbines, which is specific speed. This is one way of selection of turbines. So we focus on the specific speed of turbines in today's class. So today's our focus is on specific speed. Very important in the sense that the turbines classification is depends on that. Apart from that, the selection of turbines also depends on that. So what is it? It is the speed. First thing, specific speed. It is the speed of a geometrically similar turbine. A geometrically similar turbine. Please note that point. It is the speed of a geometrically similar turbine which is identical. Which is identical. In what? In shape, number 1. Geometrical dimensions. Blade angles. Gate opening, etc. But of such a size that it will develop. It will develop. This is very important. 1 kilowatt power. Please note this. It will develop 1 kilowatt power under 1 meter head. It is the speed of a geometrically similar turbine. That means it is similar to the actual turbine. Similar to actual turbine in what way? Well, number 1 is its a shape. Number 2 is its geometrical dimensions. If you take the geometrical scale ratios, it should be same. Number 3, the blade angles. whatever you maintain in the actual turbine, in this turbine also you should maintain the same. Whatever gate opening you maintain in the actual turbine, here also you should maintain the. It is not the actual turbine, it is the geometrically similar turbine to the actual turbine, which is of the same shape, which is of the same blade angles, which is of the same diametrical dimensions, but which is of same gate opening. But this turbine develops 1 kilowatt power under a head of 1 meter. It develops how much power actually? 1 kilowatt power under a head of 1 meter. Then only we call that as the basically the specific speed. This speed, when the power developed is equal to 1 kilowatt and under a head of 1 meter, so that speed of the turbine is what we call it as a specific speed of a turbine. So what is the equation for specific speed? The equation for specific speed. First letter already we know what is the overall efficiency. If overall efficiency of a turbine is eta 0, we know that this overall efficiency is equal to the shaft power divided by the water horsepower. So shaft power we write it as P divided by this water power we write it as gamma QH. So normally in this particular derivation, as we have to write P in kilowatts, so gamma QH also should be in kilowatts. So that's why I am putting it this 1000. So gamma QH give in watts divided by 1000, it gives you kilowatts. So both should be that. So the basic condition here is the power developed is 1 kilowatt power. That's why I have written that. So therefore, where P is equal to the power in kilowatts, gamma is equal to specific weight of water, which is equal to 9810 Newton per meter cube. Q is the discharge in meter cube per second. H is equal to head, right? So this is already we know. So now what I can write? What is P is equal to eta 0 into gamma QH by 1000. Am I right? So therefore, this equation can be written as P is proportional to QH. See it? Because gamma is constant, efficiency is constant, some value, 1000 is a value. So naturally, P is proportional to QH. If I call this as 1, so naturally this equation is number 2. So the first equation for us in the derivation of specific speed is P is proportional to QH. And again, we know what is U is equal to speed ratio into root 2 GH. And similarly, you know V is equal to, or I can write VF is equal to KF into root 2 GH. These two things you already know. Therefore, U is proportional to root H and V is also proportional to root H. In other terms, U is proportional to V is proportional to root H. This is equation 3. Then fourth, actually, we know that U is equal to pi dn by 60. So that means U is proportional to dn. So this is equation 4, right? Already U is proportional to what? Root h. So therefore, from 3 and 4, I can write it as root h is proportional to dn. Am I right? Or d is proportional to root h by n. So this I can write it as 5, right? Again, we know q is equal to area into velocity, right? So area is proportional to b into d, or area is proportional to d square, right? Then we know velocity is proportional to root h. Therefore, q is proportional to d square into root h. So this is again sixth for equation for us. I'm only just whatever little we know, that's I'm trying to put. Already above we mentioned t is equal to root h by n. Just see the equation. See the equation 5. So therefore, if I substitute that in the sixth equation, q is proportional to h by n square into root h. So that is equal to h to the power of 3 by 2 by n square. So this is what we will get. This I call it as seventh. So the fifth I brought it and put in sixth. So already we know the fundamental equation is equation 2 is P is proportional to QH. Therefore, P is proportional to Q means H to the power of 3 by 2 by N square into H. That is, P is proportional to H to the power of 5 by 2 by N square. So this equation is basically we can write it or P is equal to some constant of proportionality into h to the power of 5 by 5 by 2 by n square. I can call it as 8th. So finally, I got some equation for p where k is equal to some constant of proportionality. Then, as per the definition of specific speed, as per the definition of specific speed, the power developed is equal to 1 kilowatt under a head of basically 1 meter. So this is the thing. So therefore, if P is equal to 1 kilowatt, H is equal to 1 divided by, under such a case, N becomes Ns. If this satisfies, the speed becomes specific speed. So specific speed is represented by n suffix s. So therefore, k is equal to ns square. This is ninth, right? So now what you should do it, substitute in that. So therefore, p is equal to ns square into h to the power of 5 by 2 by n square. So this is the thing. So from this, what can I derive? ns square is equal to n square p divided by h to the power of 5 by 2, or ns is equal to n root p divided by h to the power of 5 by 4 square root of 5. So this is the final equation for specific speed. In this, what is ns? Ns is the specific speed. N is what? Speed in RPM. Speed of the turbine in RPM. Then what? P is equal to kilowatts. H is equal to head in meters. So in any problem, if they ask you to the specific speed, find out the specific speed, you should check for what is the speed of the turbine, what is the power developed by the turbine, what is the head acting on the turbine. Knowing these three parameters, we can find specific speed. So this is the derivation for specific speed. What is the significance of this specific speed? Why? What is the significance? The significance is actually the specific speed. Depending on the specific speed, we select the turbines. For example, I will put a table, right? The specific speed. If I don't write anything, please remember I am talking about SI units only, right? And what is the type of turbine you prefer? Type of turbine we prefer based on specific speed. So if I take it first one, if the specific speed is between 8.5 to 30, right, low specific speed, I will go with Pelton turbine with single jet, with single jet. If suppose if this speed is between 30 to 50, then I will go still with Pelton turbine with double jet. That means discharge I am a little bit increasing. So this is the first one. Suppose if the specific speed is between 51 to 225, automatically we will go for Francis turbine. And if the specific speed is above 225, for example, to 860 maximum, then we go for Kaplan turbine. So that's why this is high specific speed, this is medium specific speed, this is low specific speed. So in the case of low specific speed, we go with Pelton turbine. Medium specific speed, we go with Francis turbine. We go with Kaplan turbine if the specific speed is very high. So that's why normally the general practice is in generally the trend is to select a turbine of high specific speed. Why? Why is for a high specific speed turbine, for a high specific speed turbine, the size of the turbine required is less. That means basically, so when the size of the turbine required is very less, then basically the space requirements less. When turbine size itself is less, automatically the cost will be less. And one more thing is the weight of the turbine will be less. So how many benefits you see? The moment high specific speed turbine you go, size of a turbine, I mean first initially, it I mean by runner. So when runner size is less, automatically overall size will be less. So when overall size of the turbine is less, naturally you require a less space. Naturally, the cost of the turbine is the material cost goes down. So that's why the cost will be less. Finally, the weight of the turbine also is going to be very less. So this is general practice. But is there any problem with that? Let us see when it comes actually. Otherwise, generally, when you are selecting a turbine, your focus should be that I have to select always a turbine with a basically less specific speed. This should be your objective. So kindly remember that what is specific speed, then how to derive the equation for specific speed. Once you derive this equation for specific speed, then basically the after deriving what is the significance of this specific speed, but the significance of where depending on the specific speed what type of turbine you will select and what is the general practice. So these things we have studied in today's class, and next we do some problems on this specific speed. So we will take up two problems in specific speed. So our topic is problems in specific speed. Very simple. All the problems are, let us take it. A turbine is to operate under a head of 25 meters at 200 rpm. The discharge is 9 meter cube per second. Overall efficiency is equal to 90%. Determine power generated, specific speed, type of turbine. So if I take it, the given is basically the first question is power generated. The only equation I know is eta 0 is equal to P by gamma QH by 1000, where P is in kilowatts. So therefore, P is equal to eta 0 into gamma QH by 1000. Why 1000 I put it? Always P should be expressed in terms of the specific speeds and all. P should be in kilowatts. That's why whatever answer you will get, you are going to get in terms of the kilowatts. Zero point 0.9 into 9810 into Q is 9. Head is equal to 25 divided by 1000. So you are going to get actually 1986 1986.5 kilowatts. So this is the first answer. What is the second answer? Specific speed. What is the equation for specific speed? Specific speed ns is equal to n root p divided by h to the power of 5 by 4. So he has given actually n is equal to 200 rpm into this power is equal to 1986.5 divided by h is equal to 25 whole to the power of 5 by 4. So the answer will be 159.4 basically the specific speed. Then coming to the last point, what is the type of turbine? Type of turbine which we will get actually for this specific speed of 159.4 is generally, for example, if you see it, the 159 is approximately that refers to it is between, for example, 50 to some 225 and all. So naturally, the Francis turbine, which is being preferred, right? So this is the thing. So let us go into the second problem. This problem is actually last time they have given in gate also the same problem. Kindly look into it. In a hydroelectric station, in a hydroelectric station, water is available at the rate of 175 meter cube per second under a head of 18 meters. Turbine speed is 150 rpm with overall efficiency of 82%. Find the number of turbines required. They have the maximum specific speed of 460. So what is the given data is NS is equal to 460. He has given overall efficiency is equal to 82%. Q is equal to 175 meter cube per second. Head is equal to 18 meters and N is equal to 150 RPM. So this is the data that is available to me. So with this data, what we are going to do? First, basically, I know Ns is equal to N root P divided by H to the power of 5 by 4. So in such a case, Ns is equal to this 460 is equal to N is 150 root of P divided by H is equal to 18 to the power of 5 by 4. So therefore P is equal to, if I calculate how much I am getting is here, 12,927.5 kilowatts. So this is the power available, or power available at the turbine shaft horsepower. This P is nothing but shaft horsepower. So we know power available for the turbine is also equal to P by gamma QH by 1000. Why 1000 again I am repeating telling, because is in kilowatts. So if such a case actually, now basically if I see it from this, if you observe it, what is the power is equal to eta 0 into gamma QH by 1000. So what is the overall efficiency he has given? 0.82 into 9810 into Q is equal to 175 into H is equal to 18 by 1000. If I put it, I'm going to get the power is equal to 25,339.23 kilowatts. Right now, this. So now for each thing is this much. Total power is 25,000. For each of the turbine is this much. So therefore, number of turbines required is equal to number of turbines is equal to total power divided by power developed by each turbine by each turbine. So it is equal to 25,339.23 divided by 12,927.5. 0.5. So it is approximately 1.96. So I can say 2. So this is the second. So apart from this, all the problems surround actually with one point only. That one point is specific speed ns is equal to n root p divided by h to the power of 5 by 4. The same thing can be given either in the terms of the Francis turbine or Pelton turbine also. And by doing the routine problem at the end, you can be asked actually to find out what is the specific speed. So kindly prepare these problems in specific speed. Very important concept actually, the specific speed.
Like, share, and subscribe. Hit the bell icon for more updates.